examples where so we'll start the class at around 10:05. I hope Holi was good for everyone. And the reason, good morning, Devanshi. So the reason why we are having today's class as online classes because I presume that not many people are back in campus after Holi. But today I'll be finishing the last topic of this unit, which is the Newton-Raphson Method. In one of the classes, I'll discuss some finer points, some drawbacks. If I think it's important, I'll see how we can solve nonlinear equations in two variables using Newton-Raphson method or something, and then we'll straight away go to some coding. So this week, a couple of classes I want to devote to coding of all these methods. In one class, we'll see Excel coding, how we can do all this in Excel, because Excel is also a very powerful software to solve numerical method problems. And then we'll go to MATLAB and we'll finish it. So we'll finish this unit, and then we'll start with the system of linear equations. Whatever we finish till the end of maybe 11th quarter with the start, so around 7th or 8th April, whatever we finish till then will come in the exam. So start revising and start practicing problems. I will, if you want, I will upload a pirated book here, Anger and Jan, but I'm like kind of, I don't feel good about putting pirated copies. In case somebody wants to come, they can bring their pen drive and I can just give them the pen drive and they can do whatever. So I will be available in the office after 12:30. So you guys can come just before lunch and collect it. Okay. Let's start the class now. So I hope that this is visible to everyone. One person can confirm.
Yes, sir.
Thank you. Okay. So I'll start the class by answering a question that was asked on Saturday or Sunday. Like, how is secant method and regular falsy or false position method different? Because the formula to evaluate the next approximate root is the same. Well, they're different because one could say that secant method is much like a marching method. It doesn't care about whether the root lies in the interval. So you just take any two arbitrary values of x1 and x2 and you start running the algorithm by calculating x3. And once you calculate x3, you check for fx3 equal to 0 or about some value which is less than some epsilon that you've chosen. And then the next interval, if it doesn't satisfy these conditions, the next interval becomes x2 and x3. Then you calculate x4 and then you check the same conditions, fx4 equal to 0 or less than epsilon. If it is not satisfied, then the next interval becomes x3, x4. Then the next interval will become x4, x5 and so on. So it marches. So it could march towards the solution or it could march away from the solution. We don't really know. It is faster, but that is it. In regular falsy method, we take two x1 and x2, we check whether the root lies between them or not, and then we evaluate x3 by the same formula. And then we check if fx1 into fx3 is less than 0, then the root lies between x1 and x3. So it's like that. So false position method is in methodology pretty much same like bisection method, except that x3 is evaluated by a different formula. Secant method is a marching method in the sense it doesn't care whether the root lies in the initial assumptions or not. It will evaluate x3 same as false position method, but then it will not check whether the root lies in between them, and then the interval will be marching x1 x2, then x2 x3, then x3 x4, then x4 x5, and so on till you satisfy the condition fx n is equal to 0 or less than epsilon, something. So that is basically the difference. So there is a fundamental difference, and of course, false position method or regular falsy method will always guarantee a root, but secant method may not always guarantee. All right. So now let's look at Newton-Raphson. So this is the fourth and the fastest method. So there are some points about it that I want to talk about. First is it uses only one approximation. So one thing becomes very straightforward from this sentence is that there is no notion of interval where the root will lie. You will choose one assumption and based on that you will proceed. So you can either converge towards the root or you will converge away from the root, basically, right? So using only one approximation. Second is this is the fastest method. And third, it is very sensitive to the initial condition. It is very sensitive. That means if you choose some arbitrary initial condition, you may not approach the root or you may not converge to the root. Okay. So that is what it is. Let's proceed. So these are three important points that you must know. Of course, there are some shortcomings in Newton-Raphson also. One of the shortcomings is that it is very sensitive to initial conditions. There are some others which we will discuss in the class and which we will be winding up our discussion on these methods. So fundamentally, the problem is the same. We have fx equals to 0 and we need to find the roots. We say that x0 be the initial assumption. Initial root assumption. Okay. Further, let h be the small increment such that we say that let be a small increment such that we have reached the root which is fx plus h equals 0. Okay. So we say that let x0 be the initial approximation and then let this approximation be such that we are not exactly at the root. But if we take a step h more towards some root, then x naught plus h is a root. So this condition should fundamentally satisfy. So we're basically saying that x naught plus h is a root. We assume that. And from here, what we do is we expand using Taylor series. I should not say equal to root, I should say nearly equal to the root. We take Taylor series. You expand about x naught. Okay. So what is the expansion about x naught? It's very simple. So we have f x naught plus h is equal to f x naught plus h x naught plus h square over 2 factorial f double dash x naught and so now since h is much less than 1 because it's a small increment, all powers higher than h, meaning h square, h cube, h of 4 and all those powers can be neglected. So since h is much less than 1, h square and higher powers higher powers in h I should probably write it like this. H square n terms with higher order and be neglected. So if that is the case, then fx naught plus h is simply equal to fx naught plus h f dash x naught, and this is nearly equal to 0 according to this condition. So if that is the case, then your h is nothing but f x0 divided by fx dash g, right? So if this is the case, then we can say that since we chose an initial approximation as x0, then the next approximation we chose was x0 plus h. So which fundamentally means, this implies that we began with x0, then the next approximation which was x0 plus h can be written as x0 minus fx0 over fx dash 0. Then the next approximation, let us call this as x1. Then the next approximation x2 will be x1 minus fx1 divided by f dash x1. Then x3. And every time you're going to check whether, so here you will check if fx1 is equal to 0 or it is less than epsilon. Here you will check. And if this condition is satisfied, you don't need to go to x2. Then if they are not satisfied, then you go to x2 and then you check this condition or less than epsilon. If that is not the case, then you evaluate this function. And so in general, you can say that Newton-Raphson method works with this iterative formula. So this is the iteration that is going to follow, and you will also check if fx is equal to 0 or less than some epsilon that you choose, and then we proceed. So this is basically what we do. Newton-Raphson method is all about. And you can see that there is just one approximation that you begin with. So let's solve some problems and quickly finish this. Okay. So I have a couple of problems with answers, but I would want the class to participate in the sense that I would ask you and you will evaluate and let me know. Okay. So let's look at this example. X cube minus 4x minus 9 is equal to 0. I want you to find out one root which lies between 2.625 and 3. Okay, so you have to find the root which lies between this. It would not always be that you will be given an interval, but I'm just making your life easy today that I'm giving you an interval. So let's proceed. So let's say, so fx of course is x cube minus 4x minus 9. Then f dash x is 3x square minus 4. Okay. Now let us assume that the initial assumption be 2.9. Okay. So if I choose this, then I know that f, so this is the first equation, 2.95. What is this value? I want people to tell me what is this value. And I want them to tell me what is f dash 2.95. These two values. I'm waiting for an answer also. I don't have it. I can't move further. I just have the final values. I would want you to tell me. Please say instead of typing if you're typing.
Sir, f of x would be 4.87.
Just a second. 4.
872375.
Okay, and then f dash 2.95. You simply have to substitute x as 2.9. I'm sorry?
Sir, 22.1075.
2.
हाँ सर 221075.
ये पॉइंट कहाँ लगेगा?
22.1075.
अच्छा 22.107. 107. Okay, great, thank you. So that means x1 is going to be 2.95 minus 4.8723 divided by 22.107. Please tell me what is x1.
सर 2.73.
थोड़ा ज्यादा डेसिमल बताते तो अच्छा रहता. 2.7
2.72960 sir.
96. Thank you. Yeah. Okay. So now, after this assumption, you will check fx1, which means you will check f 2.7296. What is this value? Yeah. So check this value and tell me, what is the value? Is it approaching 0? Something. We have not chosen any epsilon right now. We'll just simply check whether it is 0 or not. So Forget about epsilon right now. Epsilon will depend whether I want you to give me the answer up to 3 decimal places or 4 decimal places. So if it is 3 decimal places, then it will be 10 to the power minus 4. If it is 4 decimal places, it will be 10 to the power minus 5, things like that. But you can just tell me what is this value.
0.4190.
0.4190. Yeah, so it is not very less. It's comparable to 1. So we need to go further. So now your x1. So now we start. Now second iteration starts. Now your assumption becomes 2.7296. Okay. So you would have to calculate 2.7296 function में whose value is 0.4190 as suggested. Then the second is f dash 2.7296. What is this value? I want somebody to tell me.
Sir, 18.352.
18.352. Okay, great. Thank you. So now x2 is going to be 2.7296 minus 0.4196 divided by 18.352. So your x2 will come out to be what? It will come out to be 2 point something, right? 2.7 भी शायद होगा.
2.706.
2.706?
8.
8. Okay, thank you. So this is what x2 is. Then you again check for fx2, which means you check for f 2.7068. And tell me what this value is.
Zero point zero zero four three.
0.0043.
0043.
So what we can kind of stop here if we say that we are looking for something like 2 decimal places or 3 decimal places because it is a small number. But let's say that we go one step further. Let's say that we choose to go one step further. So x2 is 2.7068. You can see from an order which is comparable to 1, you are straight away in one iteration coming to something which is of an order of 10 to the power of minus 3, 4.3 into 10 to the power minus 3, right? So you are converging very fast towards the solution. That much is clear. So if x2 is 2.7068, then f 2.7068 is a value which we know, which is 0.0043, and then f dash 2.7068. If anybody can tell me this value.
17.9803.
15 point?
17.9803.
Yeah. 03. Thank you. So if these are the two values, then x3 is चला लीजिए एक सेकंड 2 मिनट के लिए 2.7068 minus 0.0043 divided by 17.9802. Please tell me what is x3? I don't expect it to change greatly.
Yes, sir. 2.7065.
Yeah, 2.7065. So up to 3 decimal, we have already reached the solution. It is 2.7065. You can stop here. But अगर आप एक बार और निकालेंगे तो you will see that the next solution will also be 2.7065 correct up to 4 decimal.
Yes, sir. This means 0.
Yeah, we can stop here. So this is basically the solution. You can check fx3. What is this value? Just for argument's sake, what is this value? इसका क्या वैल्यू आएगा? This should also be somewhere similar to this value only. तो कोई बता दे तो मैं वेट कर रहा हूँ.
Sir, fx3 is 0.
हाँ, 0 आ रहा है. ये आ रहा है. अगर ये आ रहा है तो we will just stop here. क्योंकि अगर आप इसको फिर से करेंगे, we will go to the next iteration, we will keep on getting this value, because if you look at it, this term will be 0, right? So this term will become 0 because fx, if you calculate x4, it will be x3 minus fx3 divided by f dash x3, so fx3 will be 0, so x4 will be x3, x5 will be x4, and it will just remain the same. So this is it. So you stop here, and this is the solution. It's not always that it will come to 0. Just
Actually, no, sir, it's around 0.0005.
0005. Okay. So I think you pretty much converge to the root, because it's an order of about 5 into 10 to the power minus 4, right? At least of an order of about, yeah. So you can stop here. So you're getting an answer which is 2.7065 approximately. So in 3 iterations you were able to reach the answer. The only thing was that you knew the interval here, right? So if you didn't know the interval, then you could just, so we can, what we'll do is that this example and all, the examples that we do in the class, we'll do on Excel and MATLAB, and then you can play around there with the initial conditions and see how many iterations it takes. If you look at this problem, I have chosen the initial condition to be 2.95, which is somewhere in between. If I would have chosen 2.7 something, then I would have, reached the root much faster, because 2.7 is very close to 2.7065, right? So then maybe in 1 or 2 iterations I would have reached. So all that kind of all that sensitivity to the initial condition and all, we'll check once we do, programs on Excel or MATLAB. So tomorrow's class we can definitely, day after tomorrow and one class after that, we'll definitely have laptops in the class. Tomorrow's class, I would also like if how many people are reaching college, or how many people are already in college. I took a poll and a lot of people said that, let's take a offline, let's not have an offline class today. So do you think tomorrow we can have an offline class? Or maybe I should just ask this question again in a poll only.
Yes, sir, you can just ask.
Yeah, I'll ask in the poll and let's see, because generally I take whatever is the majority decision in the poll. Okay. So okay, let's proceed further, and let me just look at one more small problem. We'll just take this problem and I think you can solve it yourself. Let me give you first a practice problem to solve. The problem is x cubed minus x minus 4 equals 0. So this is a practice problem. I'm not going to solve it, but I will tell you the solution. So the root is 1.7963. Okay, this is the answer. It will come in the 3rd iteration. I'm also giving this to you. And you can start initially with the assumption of 2. So in this problem, I have not given you any initial assumptions. You have to choose yourself. That is generally not what is going to happen in the exam. I will definitely give you initial assumption, because if I don't give you initial assumption, then there is an issue, right? There will be a problem, and somebody may take 10 iterations, somebody may take 8, and it will waste a lot of time in the exam. But of course, if you're doing this on a computer, then you can not be given an initial assumption, and you can just run a code. There is another, like a smart thing that you can do. You can plot this function on something and then approach the root. Let me just show you. So suppose online plotter. So suppose you open something like this. This Desmos is very popular. I hope that the screen is visible, right? Everything that I'm writing is visible. So if I say x cube minus x minus 4, right? So now you can see where all this curve cuts. So if you look at this point is 1.7960, right? So I give you an answer which was 1.7963. So you can plot this and you can see where you are in the on the x-axis where the root be. And I told you that you can choose 2. So 2 would be somewhere here. This is the second line, right? So let's just, if I expand it further, you can see that this is the solution and this is 2 here. So you can choose the solution and you'll very fast, you'll be very fast in converging towards the root. If you look at the previous problem that we did, so it was x cube minus 4x minus 9, right? So this solution, you can, so let me just see, it does not, yeah, so it cuts the x-axis only at one point. I think other solutions would be imaginary. So if you look at this, then this is 2.707, right? And we approached an answer which was 2.7065 or something. It's pretty much, and we started with assumptions, I think. So if you, let's say that you start with 5, then it may just happen that you may just go away in this direction. You may not just come here. So that all that we'll experiment and we'll play around with the code once we write it on Excel. So this is what you can see. So there are some graphic calculators also, which obviously will not be allowed in the exam. But just for practice sake, what you can do is that if no assumption is given, then you can see where you can plot the graph and you can see where the roots are, and then accordingly you can choose an assumption. In the exam, in the coding exam, I will allow such a thing, because in a coding exam, everything is at your disposal. But certainly, a graphic calculator will not be allowed in the exam which you write with the pen and paper. All right, so there is another kind of an example that I will take. This will be the last one and we'll end the class afterwards. So let's say that I say find out square root of 12, for example. What is this? Using Newton-Raphson Method. Okay. So we know that there is a number called 9, which is less than 12, and there is a number which is 16, which is greater than 12. So if I take a square root on both sides, so I know that under root 12 will lie definitely between 3 and 4, right? So now I know what is the initial assumption I need to choose. At least for these problems, you can find out. Cube root will also be similar to this. You can find out something like, if I say find out the cube root of root 12, then you'll say that there is a number called 8, and then there is a number called 27. So cube root of 12 will lie between 2 and 3, things like that. So you can do that. Okay. So how do we proceed with this problem? We say let x be root 12. Okay. Then if I square on both sides, then x squared 12. So then you have x square minus 12 is equal to 0. Now this is your expression, which is fx equals 0, where your fx is x square minus 12. So your f dash x is simply 2x, right? So you can start with this initial assumption as 3 only, and then you can proceed further. I can tell you that if you choose this as the initial assumption, then your x1 will come out to be 3.5, your x2 will come out to be 3.4643, and I think we'll just end here, because that is it. So let's just, if you need to see this also, we can check this also on the graphic calculator. So if I say x squared minus 12, right? So because we are finding square root, this will have no value because it's a under root thing should always be positive. Square root so quantity. So this is what it is. So 3.464, right? And what am I giving you? Yeah, 3.4643. So this is where it is, right? So you can check. So if you choose the condition like carefully or smartly, then you will converge to the solution very fast, very fast. In the first problem, we did only 3 iterations. In the second problem also, I told you that after 3 iterations, you will get the answer. So in the second problem, this one, you will get the answer in the third iteration. This also, I think you got the answer in the second iteration. And if you would have chosen this value to be 3.5, I don't know, maybe you would have reached it in only 1 iteration. So it depends. Okay? So that's it. So now there would be in tomorrow's class, and I'll do a poll somewhere in the evening about whether we have a class in the online mode. In that, we will discuss some shortcomings of Newton-Raphson method where it will not work. So one thing is very clear. The points where it will not work is that this will fail if f dash x n minus 1 is equal to 0, which means that the slope of the curve is 0, which means that if I draw a tangent to that point, if suppose you're iterating and then you reach a point where if you evaluate the differentiation of the curve at that point and it is 0, which means that the tangent is parallel to the x-axis, you cannot proceed further because then this is going to be infinite and then come into all sorts of problems. We'll